I don't know his name actually.
Okay.
There was one also from Japan. There is one from London as well. Yeah, I talked to him. He was doing a demo, but what's the name?
I think Piotr.
Don't know his name. Okay. Okay, we're live now.
Excellent. So I'll just try playing some audio real quick. So you can still hear that okay?
Yes, here in the room, yes.
Okay, great. Then with that, I think I'll just mute and go dark for a little bit and then come back.
Perfect. Yeah,
Nice.
that sounds good. Thank you so much, Jesse.
Bye.
Bye. See you soon.
Can you hear me? Okay, do you want to share your screen again? Okay. Do I don't know which one is better. Maybe like this.
So 5 more minutes?
Yeah, so 5 more minutes and we start.
Yeah.
It's good.
Yeah, you don't need to see my face. You can just make me a little thing in the corner.
Sorry?
You don't need to see my face. You can make me a little thing in the corner.
What was the question?
Could you speak a bit louder?
Oh, okay. Yeah, we should try the levels. I was just joking that you don't need to actually see my face. You can make me a small
Okay.
little box in the corner,
Yeah.
and that's
No,
fine.
no.
Everybody wants to see your face.
Uh,
We're going to give people 5 more minutes to get here and then we'll get started.
sounds great.
See if I can hear anybody. Okay, Jesse, are you ready?
Yeah.
Oh, good. Okay, great. Welcome everybody to the last session of the day. This is a keynote by Jesse Engel. We're very excited to have him here. You can read most of the details in the little booklet, but Jesse works at Magenta. He got his PhD at Berkeley, studying Martian atmosphere and quantum dot nanoelectronics. So of course he now works in music, and I think he's going to talk to us about music and not quantum dots, but we'll see. Jesse will talk to us for about, try to wrap up at 7 o'clock. So Jesse, take it away.
Okay, great. Thanks so much for having me. I want to also thank all of you for attending such a late session, and apologies about the timing mix-ups. I'm sorry my travel schedule didn't allow me to be there in person. It would have been great to get to meet you all, but I'm just really thankful that you give me the opportunity to present. And so I'm going to talk today. I'm coming from my research group is called Magenta within what used to be Google Brain and is now Google DeepMind. And I'm going to try to talk about this question about how to empower creativity in the area that we now exist in, where we can just push a single button and generate videos and music and all types of media. And so there's sort of a question around what role does AI have to play in the creative process, which is really the fundamental question that Magenta was founded upon back in 2016. So it's been about 8 years now. I was founded on this idea of using an open source research project to really explore, what roles can and should machine learning or AI have in the creative process. And we've always sort of thought of it in terms of music. We focus a lot on music, and really as part of the continuum of how music has evolved with technology. Specifically, as we've gone from bone flutes and acoustic instruments to having electrification and synthesizers, and then digital audio workstations. It's always changed the way that people express themselves in music itself. And so there's this question. We knew AI and machine learning was coming, but what role should AI play in this instance, and could it play? And as we've worked, we've sort of focused in on a mission of thinking about how the tools can be used to empower creativity instead of replacing it. And specifically by thinking about how the technologies exist within creative tools and how those tools can be used to expand access to music creation, and then also to enable new forms of expression. And I sort of wanted to have this talk to address sort of an elephant in the room, which is there's been massive improvements in the expressive capabilities of machine learning and AI models. So with the current generation of large language models and these sort of commercially available AI generators, does that really make all these concerns we have about design and about thinking about the role in creativity, does it make it irrelevant because we can just type in something and get music back? And the case I'm going to be making is that actually thoughtful design of these systems is actually more important than ever now. And we can think of text to music as really just the start of where you might want to go in terms of helping people explore their creativity, not the end design of how people actually want to interact with AI. And so I'm going to be thinking about doing a retrospective to try to elucidate some of these ideas. And one of the reasons is because we can really think of AI as a double-edged sword for creativity. We know we've seen evidence of the cons and the harms that can exist, where existing musical communities and practices can find themselves homogenized, diluted, and commodified by the sort of automation of the things that they develop in their communities and practices. Whereas, we wouldn't be doing this work if we didn't believe in also that there was a large upside to this too, that we can get a lot of creativity from letting people to express themselves in new kinds of ways. So established artists can find new forms of expression, but also enhancing the pool of who can be a creator as well, and making creation more accessible. And some of these things are necessarily trade-offs with each other, but in other ways, they don't necessarily have to compete. And I think it comes down a lot to views of what is the value of music. Why do we make music? And you can think of it about, are you thinking of music as a noun, or at least I like to think of it, are you thinking of it as a noun or as a verb? If you're thinking of music as this commodity that is sound waves, that the value comes from consuming it. And if the value comes from consumption, then you're increasing value by reducing the cost to produce. And so mass production, thinking of that over artistic innovation, is a way to increase value. And so you can explore that with algorithmic imitation, and even in cases of functional music and stuff, actually replacing musicians with algorithms would be the way to quote unquote capture the most value. But if we think of music as actually something that we do together as a verb, it's really a platform for people's cultural identity and for the evolution of that identity, and for finding social connection and spiritual connection among groups of people. And so we can sort of flip it on its head and think about how cultural innovation can arise through empowering individuals to make music with new forms of creative agency. And so this question about how do we get the creative agency is, how do we empower creativity and agency and not just creation? And some of the things that have sort of emerged over the course of doing this for a long time is thinking about how we can build in affordances for people to put themselves in the creative process, to build systems that don't automate everything that they do, that we do. And also how to think thoughtfully about how to respect and value existing practices and communities and how to integrate with those rather than just thinking about replacing them with new types of systems. And then lastly, also trying to keep AI weird. A lot of the early work is produced pretty strange outputs that weren't necessarily just imitating the mean of music, in the popular sphere. And I think there's a real statement to be made for how you can keep that strangeness and that bizarreness in these algorithms as a way that promotes people doing new things and not just regurgitating more of the same. And so I'm going to talk about a variety of projects that we've worked on, but sort of breaks down into these 4 guiding principles that we can sort of think about in this era of large language models, even though we're not necessarily going to be talking about some of these large language models for some of these projects. But things like integrating with existing workflows so that people can bring the creativity that they already know how to manifest. They can bring it into working with AI. Supplementing existing practices by specializing what a model does. So you leave room for people to interact with their existing practices. And then also thinking about new ways of making things more interactive. So low latency, real time, and then also rich and detailed controls that really make it so that people can add more value from their own experience and their own practice into the generation. And it's not just, oh, well, what prompt did you use? And I think having more detailed, rich interaction gives more bits of communication. And so you'll see a lot of talking about that. And finally, very importantly, is doing all this by not doing the work in a vacuum, but engaging with the creative community of artists and creative coders through open source, and then even through things like this AI song contest that we've been a part of for years. And I'm gonna go through and sort of there's this sort of we're going to try to draw some of these lessons from some prior work going back through the past 8 years, and then also recontextualize it in terms of the current work. So I'm going to talk about some of these different papers, and then we'll end up in talking about large language models and how this can apply going forward. And I also just quickly want to mention, you'll see sprinkled throughout this some of the work we've done engaging with the creative community, whether it be collaborations with different artists or putting on performances for this Google I/O show that happens each year, or directly interacting with the creative coding community through open source and the AI song contest. And then finally, if you want to, I encourage you all to try some of this out yourself. There's a website you can go to, g.co/magenta, that has a large variety of different types of demos and blog posts and code for you to check out and may be helpful in your own research and practices. So getting started, want to thinking about the role of integrating with existing workflows. And like I was talking about, the importance of doing that such that people can bring their existing practices and find ways to supplement what they're working with. And one of the other things that we've worked really hard on with Magenta is thinking about not just doing research and then sending it out to the world for someone to figure out how to use it, but really the interdependence between thinking about the research and the design. So what is the interaction you're trying to do? What's the implications on the data set and on the model? So I'm going to go through 3 examples here that I think are kind of interesting. The first one that we started with was thinking about the paradigms of synthesizers and wanting to be able to take something where there's a lot of existing technology to be able to play different notes and then change the timbre of notes with synthesizers. So we had this question of, well, what role could machine learning play in that? And could we actually learn to play a neural network and morph between the sounds of different instruments? And in order to do that, we needed to learn a latent space of the timbre of those different instruments. And be able to have a data set that is representative of individual notes of instruments so that it can take individual notes as the inputs for the model. And that gave rise to this work, NSynth, or neural audio synthesis, which in 2017, we used what was state of the art back then. So models that were autoregressive within the waveform itself to actually take music, take waveforms, and encode them into a latent space of the timbre and the pitch of the note, and then be able to use another WaveNet decoder to then take those latent spaces and reconstruct the audio. And so what's interesting then is we could, as you could do in many autoencoders or latent spaces, we could then interpolate and find the spaces between different types of musical instruments and then reconstruct the audio that came out. And we paired this with releasing a data set, a large-scale data set of musical instruments called NSynth, also confusingly named the same name, where we could then have this space to model, to constrain the model to focus on timbre. And so once we trained these models, it created a whole range of opportunities to integrate with existing workflows. So we could do things like building actual websites that allowed you to smoothly drag between different types of instruments. But we could also look at building software plugins and even physical hardware that would enable this type of interaction. So we actually could create a 2-dimensional grid of musical instruments and then allow people to move between those instruments while playing notes in a traditional fashion. And so I'm just going to play an example of that here, and you'll hear all sorts of ways that the model gets the timbres of the instruments wrong, but in a way, there's a certain charm to the weirdness of its 2017 neural synthesis. So here we go. So you get all these sort of squelchy and crackly types of artifacts, but they're in the domain of musical sounds. And we found that musicians actually love that. Occasionally I'll have musicians come back and say like, oh man, I just love that 2017 WaveNet sound, you know, how can I get that? So I think that goes to show that what's creatively useful sometimes can also be the things that technology doesn't do well, just like the drum machines, 808 drum machines, or distortion on a guitar pedal. And I want to move forward to another example. Hopefully you all could hear that example okay. I think I saw a nod, so that sounds good. So we wanted to think, well, that was cool if we could do that with timbre, but what if we could do that with the actual notes that you're feeding into the synthesizer? So could we explore latent space of musical riffs and phrases? And again, you'll see all these examples where we're pointing towards autoencoders for them. So there's this idea of taking a MIDI representation of notes and then encoding those in a latent space. And so it required a data set of riffs and phrases of these sort of 2 and 4 and 8 bar phrases we could then encode into this latent space. And this was music VAE, variational autoencoder. So it's just had that same idea of finding a vector to represent a whole bar of music using recurrent neural networks as the encoders and decoders. And so what this allowed us to do, if you'll bear with this long example, it's kind of a neat demonstration of starting with one musical phrase and smoothly interpolating to a different musical phrase by just moving in the latent space. So it's smooth in this continuous space, but in the discrete space, you'll see how it evolves in sort of a smooth way. So it'll start playing the first phrase and then the second phrase, and then we're going to hear it play, evolving from one to the other as the colors change. Cool. So you can see it sort of maintains, the key and everything, and is able to sort of interpolate between the gestures of these two different types of phrases. And we were thinking about how to incorporate this into something that could actually be useful for artists and musicians. And we actually found a bunch of different types of operations that we could do within these latent spaces, and created a suite of plugins called Magenta Studio that allowed, because of sort of the open APIs of certain software like Ableton Live, it allowed actually manipulating the compositional material within a digital audio workstation. And so this was sort of an early attempt at integrating neural networks into digital audio workstations. There's another example real quick of being able to learn inverse transformations, where we can take a given drum groove, break it down into what the specific rhythm was, and then train the model to drumify it, as it were. So it can take in a rhythm, like say of a melody, and then be able to generate a drum groove from that. And so here's just a quick example of doing that with a bass line, where it's going to play the bass line, and then we're going to extract the groove and create drum lines for it. So that's the original bass line, and we're going to use Ableton's built-in MIDI extraction to extract a MIDI file, create the groove, and then use the plugin to generate a new drum track for that, and then play it on the drums. See how So it's sort of a backdoor method to being able to create musical accompaniments. What was nice about these models is they were also very small, so we could embed them in JavaScript and release them as part of Magenta.js, which is this open source JavaScript library for doing machine learning in the browser and creative machine learning. And then that was really enabled a whole creative community of coders to build all sorts of types of interactions around these different types of ideas, and explore new types of user interfaces and user experiences, which is really, I think, an underexplored area in this modern age of machine learning, where the UX is often provided by a sole provider of the model. And so I think it's really excited to see, as more of these models become open, how can we explore different types of user interactions that might be possible, including things as strange as embedding control of the models into like a little pixelated room, and then controlling those models from, in this case, a chat, and saying secret words in a YouTube chat, and being able to control a shared experience. So looking at social interactions with machine-generated music. The final example I wanted to talk about was inspired by the idea of Rock Band, which was this video game where you're trying to play a reduced version of music, and it just plays back the original recording if you play the notes right. And so many people found that really inspirational as a user interface that people even learned to play music just from playing with Rock Band. So we asked, could it be done in reverse? And that really encouraged us to think about encoding not into a continuous space, but can you encode the 5 buttons that you might push as the latent vectors, and then take all the notes of the piano and map them into those latent vectors, so that the piano playing is actually a function of the notes you're playing and the timing that you're playing between those notes, based on a data set of piano playing. And so this was this work called Piano Genie. What was interesting is that we could then build interfaces that made it more accessible for anyone to just sort of mash buttons and be able to be performing in a sort of more similar to a real piano player. And we did a bunch of user studies that found that one of the interesting aspects of it was actually that a lot of people had stage fright about playing an instrument and all the social biases that they thought would be associated with, oh, you have to know how to play an instrument. And so people actually naturally would blame Piano Genie if it sounded bad, but then if it sounded good, they would take credit and they would feel encouraged along their process of musical learning. So I think there's an interesting lessons there in terms of how putting AI in terms of traditional musical playing can actually help with some of the social problems we have around creating lines between who is a musician and who isn't in these kinds of situations. And just a quick example, we made a physical hardware controller. And so here's the first author, Chris Donahue, actually playing a bit of piano. So it's not the best piano playing you've ever heard, but it is different than just playing 5 different notes. And it was interesting to see how it evolved when we then took collaborations with professional musicians. So in this case, we were working with the Flaming Lips, and we made a different user interface, but when they played in a more musical way, they got a more musical response. So this interface was actually resistive sensors in a bowl of fruit, but you can see you're getting a very different type of interaction from playing with that.
You know, inside a bowl like that is, you know, it's like, and it depends on how bright they are. You know, when things are really bright, we know there's like a yellow and a green, and it's all a little hazy, and it's pastel. It's not as, I mean, I think it can be effective, but I don't know if it can be, yeah, 20 colors, right. You know what I mean? Do a little bit more of that, yeah.
You're up high. You gotta go down.
Wow, that's wild.
Right?
That's fun.
So they're sort of like showing ways that you can take an accomplished traditional musician and get them out of their shells and finding new ways to express themselves. And they really took this to its logical extreme, or illogical extreme, as it were, in a performance where we worked and took that fruit concept, and they put them in a bunch of these giant anthropomorphized fruits, and they had sensors, and we threw them into the audience, and people would, when they punched the balloons, they would activate the sensors. And so there's ways of creating new ways of connecting with an audience, mediated through AI, but still very much a human connection and very much weird, keeping the weird location. So moving beyond integrating, I also want to talk next about making things more interactive, and how we already saw there was interactivity in those previous things, but I also want to dive deeper into some of those concepts and how making things real time and having richer levels of control can be helpful for folks. And one of the main problems for making neural networks interactive, a lot of the things you've seen in the past have all been using MIDI as a representation, because actually generating audio with neural networks is a relatively, networks are capable of doing it, but it's a relatively expensive operation, and they're black box. It's not clear how to intuitively control that. So it's difficult to get it working in a on-device, you can run it from your browser or from your computer, and actually generating expressive audio with the networks. But we had a lot of research where we're like, well, that's when we're trying to generate the audio directly, but what if we have good priors about how signals are structured and how digital signal processing works? So what if we integrate that with deep learning, which gave rise to this work, differentiable digital signal processing, or DDSP. And the idea was to use expressive neural networks, but small ones, to control simple digital signal processors like oscillators and filter banks and noise generators, such that you can combine that together and control them in a way that no person could control. So there's an expressive control from the neural network that actually gets you a much more realistic signal than you would with a traditional synthesizer. And so the advantage is we get high quality real-time synthesis if the signals are within the expressive domain of the digital signal processors. And it can be much more efficient. It can run on CPU. It can train on just a couple minutes of data instead of hours and hours of data. And so an example of this is using it like an autoencoder. So we can take in a given instrument and extract out features from that instrument, like the fundamental frequency of a monophonic signal and the loudness of that sequence of that signal, and then run that through a neural network to control the different loudnesses and frequencies of a bunch of different oscillators and noise banks, and then filtering those and applying an impulse response to actually give synthesized audio. So this is doing traditional additive synthesis and subtractive synthesis, but controlled by a neural network now, instead of a person controlling the knobs with their hands. And what this allows us to do is really get some disentanglement, because we've built so much bias into the model. And is assuming that we can fit the data, so in this case being restricted to monophonic data, then we can actually disentangle all these different elements. And it's actually quite a white box algorithm. So you can see the fundamental frequency, you can see the amplitude envelopes that we're using for every individual note. And then you can see even the amplitudes across all the different harmonics or integer multiple frequencies of the fundamental frequency, and how they're varying in a way that no person could do by hand. And so you can get fairly realistic reconstructions. Here's the original. And then we can resynthesize that audio. And what's nice is you can deconvolve all these different elements. So you can even hear, like, here's just the subtractive synthesis. Here's just the filtered noise part. So you sort of have multiple levels of control there. And beyond that, what you can do is, if you train a model to take any series of pitch and loudness curves and turn it into audio representing a musical instrument, we can actually then transfer between different musical instruments by encoding one musical instrument and decoding with a model that's been trained on another. So here's like a violin. And then we can decode with a model, take out the pitch and the loudness, and then decode that with a model that has been trained to be a flute. Or we could even do it for singing, as in the case of, this was at the time an intern working on the project, Hanoi. He was singing Somewhere Over the Rainbow.
Somewhere over the rainbow.
And then we can take that, extract the fundamental of his voice and the loudness, and then play it as if it were a violin. So that allowed for a lot of fun interactions, and we looked at how small we can make these models. And it turned out we can make them actually quite small. So because most of the audio generation is happening from these digital signal processors, we could get the neural network down to less than a megabyte, and actually running in CPU on a phone in a browser in real time. And so this enabled us to do projects like the Sounds of India project, where we could actually reach a lot of people who didn't have top-of-the-line phones, and be able to create an experience where they could convert their voices into music for this. This was for the Indian National Day. It was just another instance also of looking at how the biases you build into your systems affect things. So since we weren't using traditional Western notation, but just fundamental frequency, it actually works quite well at capturing microtonality, as it is popular in like Carnatic Indian singing. So here's just an example of that. Here's the original input. So if you tried putting that into musical notation, Western musical notation, it wouldn't work. But here, since we're just using the loudness and the frequencies, we can then convert that into musical instruments. And so we want to make this also sort of take an opportunity to think about how we can use these technologies for education. And so we built a website, Tone Transfer, that you can go to that sort of has more educational elements about all these different instruments. You can learn about connecting to educational resources about how they work, and then be able to hear yourself expressed, any of your inputs through converting them in real time on the browser. And then finally, in terms of integrating into workflows, we not quite integrating into workflows yet. We also found that people enjoyed both sort of from a musical perspective, enjoyed how it just did one part of their process, but it was also good for memes, as the case of Hanoi here playing a cardboard saxophone.
Bow wow wow wow.
There we go. And we also wanted to push to integrate with musical workflows. Haven't got to that quite yet. I should go to the next slide before I lead into it. We did another project, given that you can take these contours, and since you're thinking only in terms of frequency and loudness contours, we could take those contours from anywhere. So we could actually take drawings and then do cross-modal synthesis by taking the contours that people draw and actually synthesizing the thought with audio. So this was in collaboration with Google Arts and Culture. And this is something I just drew last night, but you can see if it follows the contours of what you draw in terms of playing different musical instruments. So here's what ICCC sounds like. And yeah, this was a really fun thing that I think a lot of people of all different ages and musical experiences sort of enjoyed getting to put themselves, having a lot of control to put themselves in the process. And now finally, in terms of integrating into musical workflows, we went ahead to try to actually make it so you could get real-time transfer and generating a plugin, a digital audio workstation plugin, that with less than 100 milliseconds latency could actually convert inputs into, so you could play one thing and have it sound the other in real time. So here's an example of that. So what's cool about that is beyond MIDI synthesis, it really was capturing the nuances of my playing there, which was sort of enabling me to take what I already knew how to do and then use AI to expand the capabilities of what I can do, but still capturing a lot of the fine scale details of my inputs. So giving me a lot of agency over the situation. I think I'm given time. I'm just going to skip ahead and talk about one of the great things about it was that we're working on these streams of audio, but it was also a limitation. So, there's other ways we might want to interact with notes in terms of thinking of higher level representations, like traditional notes from Western musical notation. And so we worked to be able to bridge that gap with this work called MIDI DDSP, where we actually were showing that there's an interesting approach that's sort of the polar opposite of just end-to-end training of a large model, which is thinking about structuring a model in hierarchically, such that you can go all the way from high level to low level representations. So you could just train a model to go straight to audio from notes, which is nice, but there's this extra level of affordances that you get for people to express themselves if you can create and structure a hierarchy in a way that's useful to people. So here we could take look at audio and represent it like we just saw with DDSP, with these contours of pitch and amplitude. But then you could also think about how those could be segmented into, events or notes, and then how those different notes could have different types of performance attributes. So here's an example of that. This is an excerpt from Phantom of the Opera, and you can see here's the notes that are played, and here's the pitch contours and the spectrogram from the audio. And so here's the original audio. You can see there's just a little bit of vibrato, relatively legato notes being played. And we can look at, first off, being able to control note level characteristics, like being able to just change the whole pitch of individual notes, like we do for the last two notes here. So you can see here the last two notes were higher. But when you have a hierarchy, you can actually go farther and give intermediate level controls to say, I want to bring out certain performance characteristics of these events. So I want more vibrato for this long note. And I want these short notes to be really accented and staccato. So you can listen for that aspect here. So hopefully you heard it was more staccato and having a vibrato for the high note. And you can even then expose the lowest level of hierarchy if people want that level of control, like being able to draw in the exact pitch curve that you would like to see. So in this case, drawing in a glissando to go between the first two notes. So using a combination of levels of the hierarchy, we're actually able to control this phrase in various different ways, where you might not want to have to draw in the vibrato exactly note for note. You might just want the expressivity, but then you can control it at different levels of the hierarchy. And the way the system works is by having a hierarchical model and structuring things in a way so the lowest level is just like we saw before with a DDSP autoencoder that has the frequency, the amplitude, and the harmonics and the noise. The intermediate level can look at these different DDSP characteristics and then cluster them into different attributes like brightness and vibrato and attack noise and these types of things. And then the highest level, we can actually then model autoregressively the values of these performance level attributes in the notes. And so then we have a full synthesis system where we can then, even though it's monophonic, we can actually take an input melody. We used a different model here, this Bach harmonization model, to actually create a harmonization for 4 parts and then generate a full quartet by synthesizing them. So here's the intro melody. And you may recognize that. And then, so we can do that, create the harmonies, and then the model will fill in all the expressive attributes, which are then modifiable as well by the composer. And so we can apply that in an automated way as well, which can be interesting for research. Since every aspect is modifiable, we can do different augmentation strategies to then create really large data sets of synthesized music. So in this case, creating chorales of automated 1,400 hours of these generated chorales, which then can be useful for other types of musical practices and research. So here's just an example of what those might sound like. And so again, since this is a generative system, you can actually modify those scripts and generate your own types of outputs that you would want for your research, but having really fine scale control over all those attributes. One last thing I wanted to talk about as well was focusing again on, instead of automating the entire process, on supplementing existing practices by focusing on individual elements. And so building off of what I was talking about previously, a line of work that is very useful for a lot of musicians is to be able to think about the composition and the synthesis as two different elements. You know, the timbre of the notes you want different from the structure of the music. And so we can break down musical modeling in terms of this transcription, composition, and synthesis tasks of going from audio to notes, notes to notes, and notes to audio. And this has been a long thread of research for Magenta over many years, looking at these different aspects. I'm going to just briefly touch on the transcription work because I think it enables a lot of this other modeling that we're interested in, being able to provide more control, even for the case of large language models. So transcription is this difficult task of going from audio to notes. And we started off in 2017 with this onsets and frames work that really created a breakthrough by just the simple act of, instead of modeling each individual frame of which notes are present, incorporating explicit priors to understand that most notes have an onset and an offset. So predicting separately the onsets and whether the note is present, and then using that as constraints for decoding. And so using that, we got big advances in the state of the art of transcription of this pianos. And so here's just an example of Eric playing, and we'll switch between the audio of the transcription and the real audio. So you can really see the accuracy of the system. And we made that available to people through a website. And an open source model. But it sort of brings to the question of like, well, that's nice for this one data set of pianos where you have that, but what about all the other instruments? Which brings us to thinking about how we can do this for multi-track music and really multitask, taking in every possible transcription data set that we might have, which came to MT3. And so this was this idea of incorporating modern transformer technologies, sequence-to-sequence modeling, to be able to take in spectrograms and then output the tokens that correspond to the multi-instrument MIDI transcriptions, and doing this for all the sort of publicly available transcription data sets. And the key innovation here was to look at different ways of encoding simultaneous streams. As opposed to language, we might have multiple notes here being played at the same time from different instruments. And so we could decode that into a tokenization that had separate note on and off events, and then also advancing forward in time, such that you have a deterministic mapping from any piano roll to any series of tokens. And by doing that, we saw that training in a multitask manner, similar to text and other things, actually had a large improvement for a lot of the different data sets, including the low resource data sets. So this is just a small example of showing the going back and forth between real audio and transcribed audio with bad MIDI synthesizers, but for a full string quartet. And so when we have these transcription systems that are doing part of the work, it really enables people to then take music that they already know and love, get the MIDI notes, and then use that as a starting point for their creative process. It also enables us to think about training models with those transcriptions as an input. So when we think about composition or autoregressively modeling what's coming in the future. And so this is actually a little out of order, but this was the first, one of the first applications of transformers, because we were working with the original authors of the transformer paper. So Anna Huang and Ashish worked together on this to apply it to music using a similar tokenization scheme as I described earlier. And we showed that using transformers to autoregressively model these note events, we could then feed lots of transcriptions of these piano performances, and then be able to provide additional conditioning to control things like with melody and chords. So unconditionally, you could get realistic performances. But then interestingly, you could add in things like a melody control to enable people 2 levels of control, both as the inputs to be able to control the types of outputs they get, but since MIDI notes themselves are a manipulable representation, then they can take that as the starting point for their composition. So this is just an example with Happy Birthday. And since it's autoregressive, if you generate multiple times, you'll get different types of harmonizations and accompaniments. Yeah, so it sort of fits in by doing, it's not generating just the full audio, but it generates you know, chords and accompaniment in a way that could be inspirational as part of your process. Finally, I'm going to take the last few minutes and talk about the last couple years, which is really focused on using large language models, not on some of these intermediate representations, but on the audio themselves. And a lot of this work got kicked off by we were collaborating with other Googlers to Google researchers, part of Google Research. Now these people are all now inside of Google DeepMind to generate music straight from text descriptions, which is pretty a common thing for people to see here these days. And the way we do that is by tokenizing audio in different ways. So we have autoencoders to be able to take audio and be able to encode them into latent space that we vector quantize in such a way that it can be decoded back to audio. We also found it helpful to have tokens that were trained not on a reconstruction loss, but actually with contrastive losses to capture more of the semantic content and interleave those with the tokens for the acoustic embeddings. And then as a control signal, the starting place was to take a network and contrastively train it, sort of like clip or clap, but this is called music language model, so be able to, Mulan, to find the joint embedding space for the audio of the music and the text that describes that music. And then at training, what we can do is we can take audio, get the embeddings for that, for the style of the music that would correspond to the text, and then use that to predict the semantic tokens, and then use both of those to predict the acoustic tokens that can be then decoded to audio. And then at inference time, we can take text descriptions of music, like in this case, talking about the soundtrack of an arcade game, a fast piece and upbeat, get the joint text music embedding from that, and then use the language model to decode that into audio. So here's an example from that text description. And we made this available to people through a partnership with labs at Google called Music Effects, where people can go and try out text and music for themselves. And then going beyond that, working with Google Arts and Culture, we could see how we could think about this in a different way. Like, sure, we can generate music from text, but what are we doing with it? So this is a really cool instrument that we built that you could type in any name of what you want to play. And then instead of just hearing the music back that was generated, it uses that as the starting point and creates a whole multi-sampler instrument with granular synthesis and sequencing and a bunch of other stuff from the audio material that's generated. So it allows you to put a lot more of yourself into that process. And that's sort of the question that we think of when we think of text and music. You know, how do we think of this as the starting place and not the ending place? We want to stick people in the center of the creation. And so one way of doing that, we thought, was to use people's voice to really, because there's so much of a person's personality communicated through their voice. So generating music around their individual voice, which is this work, Sing Song, which has a similar music training setup to Music LM, where we're taking audio, but we're first source separating a mixture of audio into the vocals, and then taking out the mixture and finding the style embedding from that, and then generating the music that corresponds to the separated instruments conditioned on those vocals. So given your voice, you're generating the music that goes along with the voice, conditioned on style. So that's what we do at inference, right? You take in some new voice and you get the style embedding, and then you use SingSong to generate an instrumental that we then mix back in together. And so we showed that this could work both for professional singing and amateur singing. So here's an example of just taking a cappella track.
When it's all over, when we are a maid.
And then we can do that to create an accompaniment that might go along with that singing.
When it's all over, when we are a maid.
Similarly, we could do that for amateur singing, which got us really excited as well.
Et ça fait allez les bleus, on va gagner le foot à l'aide des pieds, ça va être super bien. Et ça fait allez les bleus, on va gagner le foot à l'aide des pieds, ça va être super bien. On va marquer plus de points que l'adversaire. Let's go!
And so, yeah, it was sort of these ideas of how to use large language models, but still keep the person at the center of the creation. And the biggest way that we'd like to do that is really think about making them more interactive. So it's not like you just press generate and you wait and you get a thing, but how do you increase the bits of the rate of communication between a person and a model? And we really think about making live music with large language models. And the reason we're really interested in live music is that it's approachable, as we saw with earlier things like Piano Genie. It's instantly engaging, and it's also ephemeral. Like if you don't like what you did, it's over. You know, it's more like Snapchat. It's just gone. So people, regardless of skill level, felt really much more approachable to it. And it's an embodied experience that puts you in a perceptual action loop with the music generation itself. And it's a social experience. You know, when you're generating music live, it happens in a place, and there are other people around you, and so you can share that place in that space, and it's a shared moment of creation, you know, that you can capture with recording, but it's different than the live experience. And so we worked on a model that's yet to be published, but you can play with it publicly, called Prompt DJ. It's known publicly as Music Effects DJ. And the idea here is to take Music LM, but convert it now into a real-time musical instrument where we can do streaming control. Instead of generating 30 seconds as, you know, just as a static quantity, we're generating 2-second chunks of audio that are continuously evolving in time as they would autoregressively, but now being informed by live control over the different embeddings for these different prompts that you're doing, and mixing these different prompts together to form fusions of different styles and evolution. And so a quick video demonstration of that using this technology, Music Effects DJ. So it's the DJ mode on Music Effects. I just want to show you a quick example of how you can really play and interact with this like it is a musical instrument. So this is publicly available. You can go to Music Effects DJ, g.co/lab/Music Effects DJ, and really type in anything you want and be able to sort of play and let it evolve over time. And we even featured it on the main stage with Google I/O this year. Mark Rebier did a rather over-the-top presentation of it, and as he is known to do. But yeah, it sort of opens up this door to thinking about not composing through set songs, but really creating a shared social experience. And that's where this is headed. That's where we want to go. We want to provide more detailed controls to allow people to really put even more of themselves in the experience, and to be able to learn more about musical concepts through live interaction with them. And think about, we have work going about taking in live audio inputs to be able to synchronize with people and with other agents and be able to actually play more music in real time with others. And then enable, hopefully, one of our goals is to then enable someone who might be an amateur at traditional musical instruments, but they might be able to actually sit in with a professional musician and be able to have a shared musical experience together and share those moments of feeling synchronicity and connection through sharing music and having enough control and responsivity to be able to do that. And then finally, on an education front, thinking about how we can help people to go deeper on their musical journeys by, understanding how these types of augmented instruments are really nice as a starting place for interactions. But you can see how it's like, oh, a traditional musical instrument allows you even more control because you can control all these different aspects and get people, just like Guitar Hero got people started on some of their musical journeys. AI could also be a connecting point to help people appreciate and value traditional music generation, and then also get started on their own musical journeys. And so, yeah, we can think about some of these principles that we've talked about and think about in the context of having models that are capable of generating, full songs and all these things. And I think they all still apply, how specializing models to do a certain thing enables people agency to fill in the other aspects of the work. Integrating to their existing workflows allows people to bring what they already know to the table. Interactive real-time rich controls allows people to have more diversity in the outputs and actually have it reflect more of their own personal inputs in the outputs themselves and put them in the loop of creation. And then engagement with the creative community really helps us push beyond the basic paradigms of user interaction to make some weird and wonderful things that push forward creativity instead of just leaving us stagnant in terms of recreating what's already been created before. And I think I took up most of my time, but I just want to thank you all again for having me zoom in over there and chat. And thank you, and happy to take any questions with the remaining time.
So I know everybody's tired and we probably want to wrap up at some point, but if there's a couple of questions, we've got time.
Thanks. Hi. You can't see us, just so I'm Geraint Wiggins. I'm one of the regulars at this conference. I've got a question for you, which is based on something you said early on in your talk. You said something about keeping it weird. And so the following is a little tiny bit provocative. Given that what these systems are essentially doing is building latent spaces, which are effectively statistical distributions over learned music, and then sampling from them, how do you expect to do anything original and weird?
Yeah, I mean, I welcome the provocative question. I think what you can also see there is that there's a couple things. There's, in terms of the design aesthetic and what are you building for, it's when you add enough control to the space, including like latent spaces, there's all these spaces in between that have unique aspects to them, right? There's the ability to find uniqueness in the spaces between distributions, right? Because the things that we've made in reality exist, on a certain plane of latent space. But what we do by a neural network is we fill in the gaps in between those spaces. And so there's definitely weirdness within that. But I think beyond that, it's thinking beyond just what the model outputs. But when you start to think about putting it into a part of a person's process, you're allowing someone to put their own quote unquote weirdness, their own uniqueness into the final output, because you're integrating it into their existing workflows. So they can really, just like a paintbrush doesn't make things weird by necessity by itself, but if the paintbrush doesn't do the whole painting for you, but does part of the process, you can really then explore your own expression and deviate from just the standard distribution by putting your own contributions in there. So, like for example, we did a collaboration with this band Yacht back in the day, one of the first sort of collaborations with AI and music folks making an actual like commercial album. And they made this commercial album using Music VE, but what they didn't lie on the distribution of their existing data. They had trained it on their data, but they found all these because it was only creating notes, they actually then re-recorded the music, and they used that as inspiration to push themselves off of the domain of their own music into spaces they wouldn't have normally gone, and really expand the music that they were making into sort of new spaces. And because it was sort of a warped mirror, you know, and that warping, the sort of edges, the crunchy edges of failure of these models is a useful creative inspiration. And so it's both an aesthetic appeal to try to embrace the failure modes of models as an important aspect of creative process. It's a appeal to think about systems as being part of a creative process, but not the end output of a creative process, and allowing people to put their own personalization and weirdness back into the system.
Thank you. Other question?
Yeah, hi, thank you for the presentation. My name is Andre Holzapfel, and I was just wondering, you're talking about nodes as the kind of high-level representation, and I wonder, don't you think that you might be kind of perpetuating a limitation of music technology if you kind of have that as a latent, imagined higher-level representation, because your image of the note is just basically a piano roll, right?
Yeah, absolutely. I mean, you can see there was that contrast between, you know, the DDSP models being able to adapt to microtonalities and things that wouldn't fit within traditional Western notation, whereas, you know, notes have their own bias, cultural bias with them as well. I think in another way, this is another thing that's sort of about trying to keep these systems more open as well, and allowing people to design for a diversity of users and a diversity of use cases. Because while Western music notation is a bias that's been a strong one throughout the music industry for a long time, it's also a standard, and there's no replacement for a nice standard. Like, you know, the fact that MIDI won't die because it's useful. And so a lot of people know how to express themselves using Western music notation. So we wouldn't want to limit systems to only expressing themselves that way. But at the same time, it's nice to create affordances to meet people where they're at and teach people about one useful system. But there's many possible types of representations you could create on top of things. And so I think that's sort of something we're opening the doors to allow people from different musical traditions to be able to customize systems to be aware and respectful of different ways of thinking about and controlling music is really important. And I think open source plays a large role in that.
Thank you. Yeah.
Thank you for your talk. Great stuff, of course, no doubt. I think, I don't know if I'm talking for everybody, but at least I'm really thinking how we as researchers who have great ideas, of course, but maybe limited resources can really contribute to progress in this field, where a lot of the things, are already being answered by, I think researchers and labs like you and others.
Yeah, you know, I think this is a very interesting question to think about, because I mean, the majority of the research I showed here was actually done with compute that pales in comparison to what a typical academic researcher has access to, because it's like a single GPUs from 2017, you know, very types of things. There are a couple things in terms of pre-training large models to learn off of raw acoustic audio that are difficult to do. But I think there's a huge space to think about, like, frankly, the innovations in pre-training large models are kind of some of the least interesting things in terms of what we're actually going to do with these models. And so thinking about taking existing models, like I know, MusicGen is a great example of an open source model that's been pre-trained and has been adapted by a lot of people to fulfill different types of user interactions and different types of all these different types of biases about how you might actually want to generate music. And we're going to hopefully open source a model pretty soon that I'm hoping people will be able to really run with in the live interaction domain. And I think it's such a rich space that while the labs are focused on, and the industry labs are focused on, throwing as much compute and data as possible at pre-training things, I think there's a lot of overlooking of like the UX and UI space and how that relates to the modeling conditioning information that you need. And there's a whole, that research and data interdependency and interaction interdependency I talked about at the beginning, I think it's just as relevant as ever and can be thought of in terms of, well, how can I take a model that's generally capable and now make it, have a viewpoint, make it have satisfy this interaction that wasn't thought of when someone just released one of these base models, these foundation models, as it were.
Yeah. Thank you. Very insightful.
Very, very impressive work. Thank you. One question I have is about have you considered the risks that at least some of these models, due to the way they work in decoding, inference time, sampling, there is a risk that they may be plagiarizing what they have seen in during training, and the humans who are in the loop there, they may not be even aware that the music that is produced is plagiarized. Do you have anything that controls for that, or any ideas of how to do that, to control for plagiarism, unintentional plagiarism?
Yeah, or even intentional, as the case may be for some of these companies. I think this, it's a huge topic because it starts to get into musical copyright and, the role that that's played in, the development of like sampling has become an important art form in and of itself. And the time it took for that to actually become legally legitimate, and think about ways of producing revenue streams that could then satisfy, pay artists for the back catalog when they're reused in like new hip hop songs, for example, and these kinds of things. I think it's partly a technological question, but it's also partly a social technology problem in terms of thinking about creating new revenue streams and new ways of measuring attribution and those kinds of stuff. I will say this is as you might imagine at Google, this is a very hot topic of research, and something we're very interested in exploring, because it doesn't do anyone any good if we undercut the existing revenue models for musicians to be able to support themselves, because then we're undercutting the ability of new musicians to come up and help us evolve our culture and help us connect and just allow them to express themselves. So I will say, it's not, it depends a lot on the data you're training on. And I think we're very thoughtfully, you can look at things like the AI music incubator that that YouTube is currently doing with a lot of record labels and musicians to try to establish new norms and find new ways to create credit and compensation. So there's no answers right now, but it is an area that I think when we look back, hopefully a couple of years from now, it's going to, just like, when Napster first came out and people were like, oh, the music industry is finished. There were new norms that were able to be established. And so I think we're headed in those directions, but it is a Wild West kind of time at the moment.
Thank you.
Yeah. Hi, Jesse. Thanks so much for that. Yeah, a big fan of Magenta. I've been following your work for, I think the last 5 years, and it's really cool to see where it's at. My question is related to the adoption of these tools as mainstream tools for creators. I've always thought like these tools are really cool, but I've yet to see a tool that is adopted in the mainstream as a crucial tool, like an Ableton Live sort of thing, like a Photoshop kind of thing, or even plugins within that. I think I haven't seen, even with the current wave of generative image tools and so on, nothing that is really a day-to-day tool that creatives use. So yeah, my question is, what do you think is the barrier for that to happen? I'm sure it will happen at some point, but what do you see as the main barrier for that, for those tools to become mainstream tools used by creatives?
Yeah, it is interesting. What's the, like for some of the things, like Magenta Studio has, 200,000 downloads, which is like, good. It's I don't know if it counts as mainstream, right? But there is something to be said for default settings and presets, and like mainstream tools are kind of, a lot of people use what you give them, and I think there's a lot of ways that the music industry or the music making industry is still finding ways to adapt to these technologies and finding the right way to work with them. Like we talk a lot with Ableton, and in some ways they've actually started this in terms of they have now MIDI editing tools built into, like, there's sort of algorithmic MIDI editing tools that are built into like the clips themselves. And so like this new feature in Live 12, and that's been inspired by our working together on Magenta Studio and these kinds of things. I think honestly we're entering the next year or so is going to be very interesting, because we have a lot of this sort of music generation tools that are out there that are popular right now sort of exist outside of traditional DAW, like environments and tools, and seeing the ways that we can bridge those gaps such that people can take the skills that they already know and have these workflows combined in such a way that they can put more of themselves into the generated output by creating that. We are working on a set of such tools right now. It's been announced, called Music AI Tools. I didn't talk about it in this talk, but looking very heavily at working with musicians and producers and songwriters and their workflows, and looking at how to think a little bit outside the box of just, instead of sticking a plugin in an existing workflow, how do we build workflows that are tailored to these new capabilities, but then can also find pathways towards integration with traditional tools? Because at the end of the day, you always want to put your own touch on it. And like even to quote the Drake and Kendrick Lamar feud, the viral BBL Drizzy song it didn't go viral. The AI generated one didn't go viral. It was the one that Metro Boomin took and just sped up a little bit and added a beat on top of it, and that's the one that everyone went viral, because he was able to take it and put his own spin on things, and people connected to his statement because he was a part of this social experiment that was happening, and so just the generation by itself lacked, even though musically it was fine in quality, it lacked that integration with an existing person in an existing workflow to sort of find cultural resonance, let's say. So I think that we're going to see a lot more integration, and there are some DAWs exploring this right now and stuff. But I think honestly, it's also a cultural thing about whether or not people want these tools. I think a lot of people treat DAWs like I might treat a guitar. That's the instrument that they've learned, and they take pride in tweaking every little aspect of things. And so finding a balance that allows people to still take those skills and use those skills, but then augment them and supplement them with these new capabilities, I think is it's a thing that's just different for every user base. I think Ableton users might respond to it differently than Logic users, than and so on and so on. So I think we will see widespread adoption. We're already starting to see some, and I think we'll see it in the next year or 2 for sure. But it'll be interesting to see what form it takes.
Okay, let's thank Jesse one more time. Thank you, Jesse. Appreciate it.
Yeah, thank you all so much, and thank you for staying up late. And, and I'm sure you're all very tired, but I really appreciate the opportunity to talk to you all. So thank you for having me.
Thank you so much, Jesse. This is Maria Hedblom, the local organizer. I just wanted to also say that all of our keynotes are something that we are very happy to have with us. So we also like to honor that with some material possessions. Since you are not physically here, we cannot give it to you in person. But we do want to say thank you in a way that's, leaving a mark. So there will be a post box coming eventually to you. We just need to have an address where we can send it, and then you can indulge in some Swedish folk and fairy tales by a local artist that used to paint trolls and fairies and stuff like that. So this will be coming on the, in the email or in the post actually nowadays. So thank you very much.
Thank you very much. I look forward to receiving it, and it sounds right up my wife's alley in terms of the types of things she likes.
Perfect.
All right. Thank you all.
All right, and since I have everyone's attention, there were some things left in the demo session. So I have one, what I believe is a blazer with some things in the pockets, one